On the 20th of May, 1990, the most powerful telescope ever built opened its eye for the first time, and the picture it sent home was wrong. 4 weeks earlier, the world had watched it rise into orbit on a column of fire. It was the single most expensive scientific instrument our species had ever constructed, the product of roughly $2 billion and 15 years of work. And it had reached space in flawless condition. Nothing had failed on the launch pad. Nothing had failed during the climb to orbit. The telescope was healthy, powered, and sitting exactly where it was meant to be, roughly 550 kilometers above the surface of the planet. And still, when the first starlight fell onto its great mirror and traveled down into its cameras, every point of light came back smeared. Where the engineers expected a single hard point of a distant star, they found a bright core wrapped in a faint, ghostly halo. The finest telescope humanity had ever made could not pull the universe into focus. The cause was not the electronics, and it was not the launch. The cause was the mirror at the very heart of the machine. A mirror that had been ground to the wrong shape by an amount far smaller than anything the human eye can perceive. The error measured a little over 2 micrometers at the edge, about 1/50th the width of a single human hair, and it was enough to blind a $2 billion eye and turn a national triumph into a national joke. This is the story of how a mistake the size of a fraction of a hair nearly destroyed the Hubble Space Telescope. It is the story of how the flaw was traced back to a single misplaced rod on a factory floor in Connecticut, and how, 3.5 years later, a crew of astronauts flew hundreds of kilometers into orbit to do something no one had ever done before. They went up to give a telescope a pair of glasses. To understand how much was riding on that mirror, we have to understand why we built the thing at all. Every telescope on the ground fights the same enemy, and that enemy is the air above it. The atmosphere we breathe is never still. It moves in warm and cold pockets, it churns and ripples, and every ray of starlight that passes through it is bent and jittered 1,000 times before it ever reaches a lens. That is the real reason the stars appear to twinkle. What looks romantic from a garden is, to an astronomer, a wall of distortion. It is the reason that for centuries the sharpest telescopes on Earth still delivered a slightly trembling, slightly blurred view of the cosmos. In 1946, an American astrophysicist named Lyman Spitzer wrote down the obvious solution. If the atmosphere is the problem, then we must place the telescope above the atmosphere. A large telescope lifted clear of the air would see the heavens with a sharpness no mountaintop observatory could ever match. At the time, it was close to science fiction, because we had no rockets capable of carrying such a thing, and no way to service it once it was up there. Spitzer spent much of the rest of his life arguing for the idea anyway. It took more than 3 decades for the dream to become metal. The center of that dream was the primary mirror, a disc of ultra-low expansion glass, 2.5 meters across, ground and polished by the Perkin-Elmer Corporation at their facility in Danbury, Connecticut. This was to be the most perfect mirror ever made. The surface was polished so smoothly that no bump or dip across the entire 2.5 meters rose higher than about 10 nanometers, a smoothness finer than a small fraction of the wavelength of visible light. If that mirror had been scaled up to the width of an ocean, its tallest wave would have stood only a few centimeters high. That was the pride of the program. A mirror ground to a precision almost beyond imagining, and it would turn out to be precisely, perfectly wrong. On the 24th of April, 1990, the Space Shuttle Discovery lifted off carrying the telescope in its cargo bay. The next day, the crew lifted Hubble out on the robotic arm and released it into orbit, and the machine unfolded its solar wings and came alive. For a few weeks, everything about the mission looked like the clean victory that everyone had promised. 15 years of budget battles and engineering were finally behind us, and the observatory was in space and answering commands. Then came first light, the moment a telescope is pointed at a real star and asked to make its first image. On the 20th of May, controllers aimed Hubble at a distant star cluster and waited for the data to come down. The image that arrived was not what anyone had trained for. The bright stars in the field were not the crisp pinpoints the design demanded. Each one sat inside a soft, spreading glow, as though the whole scene had been breathed on. At first there was hope that this was a simple matter of focus, the kind of thing that could be dialed out with a command from the ground. The engineers adjusted the telescope's focus, moving the mirror back and forth by tiny increments, searching for the sharp setting. No matter where they set the focus, the stars would not close down to a point. Pull the focus one way, and the core tightened while the halo grew. Push it the other way, and the halo shrank while the core spread. There was no single position where all of the light agreed to meet. And that particular behavior, that refusal of the light to ever gather in one place, told the specialists something they did not want to know. This was not a focus problem that a command could fix. This was written into the shape of the glass itself. The name for what had gone wrong is spherical aberration, and it is one of the oldest and cruelest failures in the history of optics. A telescope mirror has one job. It must take every ray of light that lands anywhere on its surface, from the dead center to the very rim, and bend all of those rays so that they converge on exactly the same point. When the shape is right, a star becomes a single, brilliant dot. Hubble's mirror could not do this. The light that struck the center of the mirror came to a focus in one place, and the light that struck the outer edge came to a focus in a slightly different place, roughly 40 millimeters further along. There was no single point of focus anywhere in the instrument, because the mirror was sending different parts of the same star to different destinations. The measurements that followed were brutal in their precision. The outer edge of the mirror had been ground too flat, by a little over 2 micrometers. It is a distance so small, it means almost nothing to us in daily life. Roughly 1/50th the width of a human hair. And yet, across the scale of that mirror and the wavelength of light, it was catastrophic. The design had called for around 70% of a star's light to be concentrated into a tiny central point. Instead, only about 15% of the light landed where it belonged. The rest was thrown outward into that faint, useless halo. The mirror was not sloppy work. It was not rushed, and it was not crude. It was one of the most precisely manufactured objects human beings had ever produced. Every part of that surface matched its intended curve to within 10 nanometers. The problem was that the intended curve was the wrong curve. Perkin-Elmer had built a magnificently, flawlessly accurate copy of a mistake. They had polished, with extraordinary care, exactly the surface they had been told to make. The care was real. The target was wrong. The question that now consumed NASA was not simply what had gone wrong. It was, how? A mirror ground more precisely than almost any mirror in history could end up so completely, so confidently, incorrect. To answer that, the agency convened a formal board of investigation, led by Lew Allen, the director of the Jet Propulsion Laboratory. The Allen board went back to the beginning, to the factory floor in Danbury, and it followed the error down to its root. What they found was almost too small to believe. To grind a mirror to the exact deep curve that Hubble needed, Perkin-Elmer had built a special testing instrument called a reflective null corrector. Its purpose was to act as a template of perfection. During polishing, the technicians would compare the great mirror against this device, and wherever the mirror did not match, they would keep working the glass until it did. The entire shape of Hubble's eye was defined by that one testing tool. which meant that if the testing tool was wrong, the mirror would be ground wrong with total confidence. And no one comparing the two would ever see a problem, because the mirror would agree with the flawed template perfectly. Inside that null corrector sat a small lens that had to be positioned at one exact distance for the whole device to be accurate. A technician set that distance using a metering rod, a measuring rod tipped with a reflective cap, and aligned it with a laser. The laser was meant to reflect off a precise point on that cap. But a tiny fleck of the cap's coating had been worn away in the wrong place, and the laser locked on to the wrong surface. As a result, the lens was set 1.3 millimeters away from where it should have been, a little over 1 millimeter. From that single millimeter of error, the false template was born, and the mirror was faithfully ground to match it. And then comes the part of the story that is hardest to forgive. Perkin-Elmer had other, simpler testing devices in the same building, and during fabrication, 2 of them had indicated that the mirror was developing spherical aberration. 2 independent warnings, quietly raised. But the engineers trusted the sophisticated reflective null corrector above all the others, and the disagreeing results were set aside as less reliable. The one instrument everyone believed was the one instrument that was broken. The warnings were there. We simply did not listen to them. The public reaction was merciless, and it was fast. This had been sold to the world and to the taxpayers who paid for it as a new window on creation. Now the headlines carried a single humiliating word: the telescope could not see. Late-night comedians built jokes around it. The following year, a Hollywood comedy hung a photograph of the Hubble Space Telescope on a wall of history's great disasters, beside the Hindenburg and the sinking of the Titanic. Members of Congress who had defended the program's enormous cost were left furious and embarrassed, demanding to know how $2 billion had bought a blurred picture. In the press, it was called a techno-turkey, a flying lemon, a monument to waste. Behind that public ridicule stood thousands of scientists and engineers who had given years, and in some cases most of their careers, to this machine. They had done nothing wrong, and yet they now carried the weight of the most visible failure in the agency's recent memory. For the young astronomers who had built their futures around the data Hubble was supposed to deliver, it was a quiet catastrophe. The observatory of their generation was in orbit, alive and useless. But inside NASA, a small and stubborn group of people refused to accept that the story was over. They had one thing on their side that the comedians did not understand. They knew, with extraordinary precision, exactly how the mirror was wrong. If the mirror had been damaged unpredictably, warped in 1,000 irregular ways, there would have been no cure and no path forward. But Hubble's error was not chaotic. It was one clean, consistent, mathematically pure mistake, repeated identically across the whole surface. The light was being bent wrongly, but it was being bent wrongly in exactly the same way every single time. And a flaw that regular is a flaw that can be reversed. If we know precisely how a beam of light has been distorted, we can build a second set of optics that distorts it by the same amount in the opposite direction, and the 2 errors will cancel. The blur can be unblurred. In other words, the engineers realized they did not need to replace the mirror at all, which would have been impossible in orbit. They needed to give the telescope corrective lenses. They needed to build Hubble a pair of glasses. Out of that idea came a device called CoStar, the Corrective Optics Space Telescope Axial Replacement. CoStar was a mechanism carrying a set of small, precisely shaped mirrors on deployable arms. Once installed, those little mirrors would intercept the distorted light on its way to several of Hubble's instruments and bend it back into a true focus before it ever reached the detectors. At the same time, a brand new camera was built to replace one of the originals, the Wide Field and Planetary Camera 2, and this new camera had the correction built directly into its own internal optics. its own tiny counter-shaped mirrors ready to cancel the flaw. The physics was sound, the design was ready, but there was one enormous obstacle standing between this plan and a working telescope. Hubble was orbiting more than 500 kilometers above the Earth, and nothing about fixing it could be done from the ground. To install the glasses, human beings would have to fly up and do the work by hand, in the vacuum of space, on the outside of the machine. On the 2nd of December 1993, the Space Shuttle Endeavour launched into orbit, carrying a crew of 7 and the hopes of an entire agency. This was servicing Mission 1, and at the time it was among the most ambitious and complex spaceflights ever attempted. The plan called for an unprecedented run of spacewalks on a single mission, a series of long, delicate operations to rebuild a telescope in space without breaking it. The crew rendezvoused with Hubble and captured it with the shuttle's robotic arm, an arm operated by the Swiss astronaut Claude Nicollier, and drew the telescope down into the cargo bay. Then the spacewalkers went to work. Over the following days, working in pairs, Story Musgrave, Jeffrey Hoffman, Catherine Thornton, and Thomas Akers carried out 5 separate spacewalks, more than 35 hours outside the spacecraft in total. The work was punishingly difficult. These were astronauts in pressurized suits, their hands buried inside thick gloves, trying to turn small fasteners and handle sensitive optics, while moving at nearly 28,000 kilometers an hour around the planet. To make room for the corrective package, they had to remove one of the original science instruments entirely and slide CoStar into its place. They installed the new Wide Field and Planetary Camera 2. They replaced failing gyroscopes and fitted new solar arrays. Every motion had to be careful, because a single scratch on the wrong surface, or a component forced into the wrong position, could turn a rescue mission into the final chapter of a failure. And through all of it, no one on that crew, and no one on the ground, actually knew whether it had worked. They were installing a cure designed on paper for a flaw measured from 400 million kilometers of distance. The corrective mirrors could not be tested until the telescope was sealed, released, and pointed once again at a star. The astronauts closed Hubble up, lifted it out of the cargo bay, and let it go. Then everyone waited. The answer came in the middle of January 1994. Hubble was aimed at a distant spiral galaxy, and the new images were sent down to Earth, and the people who had lived for 3.5 years under the shadow of the blurred mirror gathered to see what the glasses had done. The galaxy that had once appeared as a soft, fogged smudge now snapped into breathtaking clarity. Individual stars stood out as clean, hard points of light. The spiral arms were sharp. The halo was gone. The correction had not merely helped, it had worked almost exactly as the mathematics had predicted, delivering the crisp, jewel-like vision that had been promised at the very beginning, back before the world had learned to laugh at the machine. When NASA presented the before and after images to the public, the change was so obvious that it needed almost no explanation. The techno-turkey was dead. In its place was the telescope everyone had been promised, finally able to do the one thing it had been built to do. It could see. What Hubble did next rewrote the textbooks. It stared into a single, nearly empty patch of sky for days and revealed thousands of galaxies where the eye had seen nothing, carrying our vision back toward the dawn of the cosmos. It helped measure the true age of the universe and narrow it down to around 13.8 billion years. It gathered the evidence that the expansion of the universe is not slowing down, but speeding up, driven by something we still cannot fully explain and have named dark energy. A machine that had been mocked as the most expensive mistake in the sky became one of the most productive scientific instruments ever built, and it earned that place because a handful of people refused to give up on a flaw measured in micrometers. The lesson sits uncomfortably close to home. A mistake far too small for us to see, born from a single millimeter on a measuring rod, almost erased 15 years of work and $2 billion in a matter of weeks. And it was undone not by a miracle, but by careful mathematics and by human beings willing to fly into orbit and fix the thing with their hands. Hubble is still up there today, still working, decades past the life it was designed for, slowly circling a world that once called it a failure. But the telescope built to succeed it looks even deeper into the dark, into an early universe that Hubble could only glimpse. And out at that frontier, it keeps finding things that, by every rule we thought we understood, should not be there at all.